But okay, so in this talk, I'm going to look at what life is and the chemical reactions that take place. I'll then take a look at some ideas about how we might imagine there were natural chemical reactions that eventually ended up with the complex chemical reactions we have in life. Now, in doing this, I'll be drawing from the writings of Professor Nick Lane, in particular, the book, The Vital Question. There we are. Okay, so that is The Vital Question. Okay, and there's also this book called Pred.text. Now, that's a Sydney activist predator from like 10 to 15 years ago. He's unfortunately passed away, but he had some very interesting ideas about information and how it related to chemical compounds. So I actually drew some inspiration from this gentleman as well, who's sadly no longer with us. Now, along the way, I'm going to outline my particular approach, which emphasises protein formation, deep ocean carbon dioxide, and adaptation. So anyway, let's have a bit of a look at what happens in a cell. Okay, so there are our cells, and we have a eukaryote and prokaryotic cell. Okay, so there we have our different cells. Now, the prokaryote on the right is a more simple cell, and the eukaryotic cell on the left is a more complicated one. Now, importantly, these cells use DNA to form proteins or peptides from amino acids, and they then prompt or catalyse chemical reactions within the cell, including reproduction of the cell and reproduction of DNA. Now, we can actually have a few views of DNA. There's a static view of our spiral DNA, and there's one where it is rotating. So DNA actually has, there we are, actually has these sort of 4 different components to it. So it's built up as a spiral chain, and the sequence of those 4 components encodes proteins. So that's how the cell knows what proteins it needs to make. Now, a cell takes in energy and uses it to maintain information and a complex set of chemical reactions, which maintain a metabolism, information, and reproduction. Importantly, it uses DNA to form proteins or peptides from amino acids, which then prompt or catalyse chemical reactions within the cell, including reproduction of the cell and reproduction of DNA. So as I've said, DNA has got those different base pairs, 4 of them, and it's the encoding in the DNA that tells the cell what to do, what proteins to make. Now, this information is copied from the DNA to the RNA. That spirals a bit, but not in the same way, and then the RNA is finally used to make the proteins. Now, amino acids is the next step in the chain. Now, there is an archetypal amino acid. Now, you can see over at this end is the acidic end, that's the organic acid end, and here is the ammonia end, which is the alkaline or basic end. So an amino acid has both acidic and alkalinic elements to it. So now there's about 20 different amino acids that are used in eukaryotic cells. So you can see there's a range of them. And I think they're somewhat different in prokaryotic cells, but these are all the amino acids you have. You combine them together into proteins, and then the proteins catalyse, or put another way, coordinate other reactions in the cell. Now, that includes extracting energy from the surrounds to form ATP, which is a major molecule in the cell which is used to store energy, and it's used to fiddle with the amino acids. And then, of course, you have breaking down external chemical compounds to form more basic elements that you then reassemble into useful things within the cell, and you make cell walls, and obviously you also copy the DNA for reproduction. Now, according to Professor Lane, the earlier book that I showed you, the fundamental thing about a cell is that it does 2 things. One is it sets up a protein gradient by various different means, and then it uses that protein gradient to basically make ATP. Now, over here, you can see here is the thing that is using the protein gradient. Now, a metaphor for this is that we have a dam, okay? And the dam has got a water wheel and a mill. And that water wheel and mill is over here. This is this part. And pretty much all cells do that, okay? Now over here, this electron says it's extracting energy from the environment and using that to move these protons or hydrogen ions to this side. So it's using those electrons to fill up the dam with water. And it then uses that water via the water wheel and mill, using this component over here, to make ATP. And the way that you get this electron to form the gradient, there's a lot of variation in that. Obviously, we can eat stuff and process that. Plants will use chlorophyll and take light to do that. Now, one interesting thing is you might have seen these brown muddy deposits around riverbanks and concrete, and that's actually iron-eating bacteria. So you wouldn't think it, sometimes you might think, oh, it's yucky, icky, brown-coloured pollution, but no, it's actually bacterial growth. And you can actually have these iron-eating bacteria growing in pipes and causing problems. It's one of the things that you can have happening. But the point of this picture is there's different ways of extracting energy. Although there's a lot of range of them, what you do is you get free electrons. You then use those free electrons to make a protein gradient, which is like filling up the dam with water. And then everything uses that proton gradient to make ATP molecules, which the cell then goes off and does stuff with. And that is like a water wheel and mill. So that's Professor Lane's story. Now for him, the challenge is how these proton gradients are built up. He talks based on observations about how cells currently use proton gradients. We might think about what stepping stones might have led us to where we are now. For me, though, I wonder if rather than current approaches to the cell suggesting what might have come before, early life and its precursors ran off a totally different set of principles, where the hints about these early approaches have been pretty much erased. Much as like you might have a finished building. When the building was constructed, there had scaffolding. And once the building is finished, there's no evidence that you once used scaffolding to do that. So in my view, I'm saying there might be ways of doing life before there was life that have been completely lost to the biological record. Now, Lane, he does actually suggest that if no current form of life uses some chemical mechanism, it doesn't work. I'm saying, no, maybe there were things that worked, but they were made so obsolete by later developments that there's no record whatsoever of them in current life. We can't find it in fossils or anything like that. So that's my scaffolding metaphor. Now, there's what's called the central dogma of molecular biology, is that DNA makes RNA, and then RNA makes protein. And then protein coordinates or catalyzes chemical reactions in the cell, but protein doesn't store information. Now, it's in my contention that in times past, proteins, or what might better call peptides, did store information and made other peptides, but that process has long since been superseded. It can be said in limited cases, protein assists in the folding of other proteins, but proteins never directly create other proteins, and in that sense can't be said to store information. Now, if this was in fact the case, how is it that all evidence has disappeared from contemporary life? Now, in this case, I use the concept of adaptation, which Professor Stephen Jay Gould identified as the wheel of fate. Now, in his conception of evolution, evolution was sometimes based on fortuitous accidents rather than incremental improvements in the face of survival pressures. So there's some accident, some discovery. And obviously I'm using words like accident and discovery, and philosophers of biology will slap me on the wrist and say evolution doesn't have a goal. I'm sort of basically forcing human words onto this, but it's the best way of communicating these ideas. Now, let me give you what's a classic example of what Stephen Jay Gould talks about. Now, here are some plankton, okay? They're bacteria that are in the ocean. They're coloured green because they have chlorophyll, so they actually feed off light in the atmosphere. But at some time in human history, we had an asteroid strike, and that made the sky dark, maybe for 3 years, maybe for 10 years, maybe for a very long time. And one of the things is most of the plankton died because there was no light for them to operate with. But some of the plankton survived. Now let me tell you about the plankton that were hypothesised to survive this meteor strike where the whole sky went black. They were the plankton that could hibernate over winter. So for about 3 months of the year, they shut down. And if you have the chemistry to shut down for 3 months, there's a good chance you can shut down for 3 years or 10 years and then wake up when conditions get better and there's light. So notice that in evolutionary history, these things evolved to cope with the seasons and things cooling down, less light, so we go into hibernation. Because they were able to hibernate, that meant that they were, in a sense, by accident, able to survive that asteroid strike which sort of made the sky black. So that is the story from Stephen Jay Gould.
Is this just a made-up scenario?
My understanding from Stephen Jay Gould is that this is a good example of that in their fossil record you can say what plankton survived the supposed meteor strike. It seems that it was a subset that were able to hibernate. Right. And let's just say a lot of things were wiped out, a lot of plant and animal life were wiped out, but some things survived, certain sorts of plankton survived. And it's my understanding now, Stephen Jay Gould does actually say this sort of thing happens all the time. You know, there's stories in Hitchhiker's Guide to the Galaxy about how crazy things happen all over the universe because there's so many things that are possible. But in Stephen Jay Gould's view, a lot of evolution is opportunistic accident rather than this sort of arms race of things slowly getting better in the face of survival pressures and so on. And yes, that does happen, but Stephen Jay Gould emphasises what he calls the wheel of fate, accident, possibilities. So now, some parts of my story are more hand-waving than others, and I have to put up my hand and say this. Now, it's my speculation that DNA and RNA originally helped with peptide formation, with peptides themselves doing the heavy lifting. But over time, it was found that because DNA had a spiral character, it was better adapted to storing and reproducing information, and it was then that DNA specialised in storing information, while peptides specialised in making chemical reactions happen. But there are some rules, oh goodness me, what did he write? The gentleman who wrote The Serious Sociology. He says that every system gets
Wilson?
Spencer, I think it was, yes. Spencer, who wrote the Serious Sociology.
Okay, way back.
Way back, yes.
Okay.
Now, he was saying that any system is obliged to get more complicated. Once upon a time, the leader of a tribe did everything, led people into battle, adjudicated disputes and so on, and as time went on you had people who did the law, people who led the military and so on, and those people had to communicate, but equally they were able to sustain a larger population. In the same way, we might say that when the chemical reactions, when life figured out to specialise, let's have DNA do this, RNA do that, and proteins do that, it became more effective. But there also needed to be communication. That's one of the things that I think it was Herbert Spencer said, that basically complexity means a greater overhead and a greater need for communication. Anyway, so that's one story there. Now, I've shown you the DNA spiral, but which I think is important to information storage. But one of the things about that DNA spiral that you might not be aware of is that it's not a perfect spiral, right? It's certainly a stable spiral. But if you look into the details, those molecules that I showed you in those subunits, perhaps I should say, in the DNA molecule, there's a little bit of stress and strain in that molecule, a little bit twisting, a little bit strains and so on. So they don't match up exactly. So in a sense, this molecule was not ordained, it was not designed. I guess obviously it's Darwin Day, we're going to push back against intelligent design, but only stretch the imagination. But the thing is, if you look at evolution, there's so many bits of evidence here, there, everywhere, that it's a bit of an ad hoc pushing things together. And you could say the DNA spiral works as a spiral, but it's more like a tradie that's made a construction and right at the end he whacks something together to make them fit, right? That's more like what the DNA molecule is. It's telling us that there was a time in the past when the chemical reactions were, in a sense, searching for something that fitted together moderately well. And DNA was a moderately good spiral. sufficient for the job, but it wasn't ordained, it wasn't designed, it was accidentally found. And again, some philosophers of biology will say that find and goals, and that's not what evolution does, but hopefully you get the idea of what I'm saying there. So apart from information storage, presently as DNA, you do need to have energy and ways of storing it when needed, and that includes the proton gradients that I mentioned earlier, and also the ATP molecule, which provides energy more generally, and it also activates amino acids, which I'll get to. So we'll now focus on amino acids. These are molecules which can be linked together. These are molecules that can be linked together or polymerized, and they're pretty flexible in their behavior if you get the balance between acidity and alkalinity right. As I say, amino acids have both acid and alkaline components in the same molecule. But before you have amino acids, you can worry about the things that we knew were in nature at the time: hydrogen, carbon monoxide, and so forth. Now, the Muller-Urey experiment from long ago put these things together, generated electrical sparks, and synthesized amino acids from things we could reasonably expect to be in the atmosphere at some time in the Earth's past. So here's a diagram of that. You can see here's our chamber. It says they've got water, methane, ammonia, hydrogen, carbon monoxide with sparks, and it circulates around, and as a result of sparking this mixture, you do actually get amino acids. Now, now, one of the problems is, though, while you can imagine a situation where you can make these amino acids, it's very difficult to then imagine a situation where you actually join the amino acids together in proteins or peptides. Now, Lane sees problems with the formation of amino acids in terms of what's needed to react carbon dioxide. Now, Lane's approach here is to actually use I think that's one of the experimenters is standing next to not the original, but a rough duplicate of the experiment they originally used. Okay, and here is Lane's approach to things. So over here on this bottom side, you actually have an alkaline medium, and that means the alkaline medium releases electrons, and the electrons travel through the semiconductor layer to an acidic environment, and they then, activate our carbon dioxide, which then reacts with the acidic hydrogen, and you actually get organic acids and things coming out. So notice the Muller-Urey experiment was saying, let's use sparks. So Lane is saying, let's have superconducting layers, or I should not say superconducting layers, semiconducting layers between an acidic and an alkaline environment. And with that, you can actually have stuff that prompts carbon dioxide to react. So carbon dioxide is actually something that's quite difficult to get things reacting. Now, I do actually prefer a different approach. I want to go back to the Muller-Urey experiment where you actually have lightning at the bottom of the ocean, right? Oh. So how might you have lightning at the bottom of the ocean where you assume hydrothermal vents will provide the hydrogen and carbon dioxide? Now, my secret sauce here is supercritical carbon dioxide, okay? Now, when you pressurize, be it water or carbon dioxide enough, it starts to happen really weirdly. Now, I'll talk a little bit about supercritical water. If you compress water enough, it will go supercritical. What will happen then? It's as dense as regular water, but it flows like a gas. And supercritical water will actually absorb enough oxygen that you can have a flame underwater within the supercritical water. Now, of course, to call it liquid water is, it's not a liquid in the way we understand it, but it's very high pressure and very high temperature. You could never see it. You could maybe see it through glass if you were keen, but you can never experience a supercritical water. Now, but
it's there now.
Oh yes, you do have stuff called supercritical water. If you want to pressurise water enough, you can get it. The problem with supercritical water,
from water pressure.
Oh well, you might get supercritical water about 11 kilometres down in the ocean, right? It's not impossible, but it's also very high temperature and it's a very vicious chemical environment. Okay, yes, question?
Does that mean that at the bottom of the ocean is still generating different kind of new molecules?
Well, I will get to that, but I don't believe you get. You could maybe get supercritical water at the bottom of the ocean, not impossible. But mostly my story is that in earlier times when the Earth was more geologically active, it was more possible to get supercritical carbon dioxide. You can't get it these days, might be very accidental exotic conditions. So one of the things I'll get to, one of my magic wands, one of my secret sources, if you want to say, is to say in geological past things were very different and we're able to do things then that we were not able to do now. Okay. So I talked about supercritical water. Now there's also supercritical carbon dioxide. Now interesting thing about supercritical carbon dioxide, they have tried to use it as an ingredient for dry clean, but static electricity builds up, right? That's a problem when you try to use it for dry cleaning. But if you think about it, static electricity is also in other ways it is an opportunity. Now, okay, we've got that one there. Now that, I think in the US they call them wildfires, here we call them bushfires. But you can actually have what are called pyrocumulus cloud formations. You have a bushfire, it generates a lot of smoke, the smoke goes into the atmosphere, forms a cloud, and that cloud can even form lightning, right? Basically particles moving around. So I am saying at the bottom of the ocean, we can have something like pyrocumulus clouds forming sparks, and those sparks can then be the input into the Muller-Urey experiment. So let me see. So there's that one. Okay, underwater volcano. Yes, that's another possibility. All right. So now, how could pools of supercritical carbon dioxide form? Now you have carbon dioxide coming out of deep sea vents forming a supercritical layer. So here is my diagram of how we might get a trench with some supercritical water at the bottom. Notice that there's a few secret ingredients you need to actually have supercritical carbon dioxide at the bottom of the ocean. One is that you need to get a temperature of about 31 degrees Celsius. The problem is the bottom of the oceans are all about 4 degrees Celsius, at least currently. But if we imagine that in geological past, there might have been oceans, bottoms of oceans that are about 1 kilometre down and are actually about 21 degrees Celsius. Then, we also have our hydrothermal vent. The hydrothermal vents put out about 300 degrees Celsius. That could actually warm our carbon dioxide to the point where it's 31 degrees C, becomes supercritical, and the things that I'm wanting to have happen. And notice over here I say geothermal or radioactive heating. Now, one of the things is that our Earth does actually heat up from radioisotope decay. Uranium forms helium. That's why we have helium in crude oil. So some heat comes from radioactive decay. And, if we imagine in times long past, maybe there was a lot more radioactivity in the Earth from radioactive decay warming things up. Also, there's what's called the Oklo reactor. I don't have any particular references to that, but there's a story that if you go back far enough in geological time, there were natural uranium deposits where the concentration was actually big enough to form a nuclear reaction in the uranium ore body, right? That's called the so-called Oklo nuclear reactor. Now, there's a few things to make this happen. I sort of say the Earth's geological past, maybe so many things are possible. I have an ocean floor and a trench here. Maybe it's actually like a big basin of kilometres wide, but there's a rim so whatever heating doesn't leak out. But equally, maybe there's a volcano, maybe there's an Oklo style reactor heating things up. You want to get things about 21 degrees, and then you only need to heat them another 30 degrees and you'll get your supercritical carbon dioxide. So that's my particular speculation there. Now, as I say, the final source of heat and carbon would be the black smokers or hydrothermal vents. At the present, they occur from about 1.5 kilometres to 3.5 kilometres, and they put out water at 300 degrees Celsius. So, one of the things of geological debate, obviously I'm not that familiar with Earth's geological history and what is possible. I can only say there's so many stories about the Earth being, the Hadean era, like it's hot, it's magma flying everywhere, all that sort of thing. If you imagine you had both magma and some water, you could imagine some very exotic things going on in geological past. We've also had super volcanoes a whole heap of crazy things if you actually go into the Earth's geological past, but we're actually relatively settled these days. Okay, so now that we're thinking of amino acids, we've made our amino acids, or how do we actually form them into peptides? Now I'll go into the reactions that we normally have for forming peptides. Okay, now so here's a bit of chemistry for you. I hope it's not too bad. As I say, over here we have the acidic end of the amino acid. Over here we have the alkaline end of the amino acid. This is an organic acid. This is a bit of an ammonia molecule. And what happens is that OH there joins with that, and that comes out as water, and then you have this bond here between the carbon and the nitrogen. So that is how you take amino acids and form them into a peptide. And notice you've got this water over here. Now the thing is, what that water wants to do, it actually wants to go into the bond here and return things to the original configuration. So you're creating water, but water hanging around actually gets in the way. Now that's why one approach to the formation of life imagines wetting and drying cycles. Okay, so you imagine there's pools on the surface of the Earth, there's evaporation, they dry out. That means the water leaves, becomes more concentrated, the activity of the water diminishes because the water wants to spend more time in surface tension on the surface, not so much participating in reactions. So you will have this reaction, it'll put out a bit of water, but because there's such a low concentration of water to start with, it will be a stable thing. Or in chemical terms, we say there's an equilibrium constant and it's pushed in the direction of having more water there when you have a shortage of water to start with. So that is the wetting and drying cycles. Now, so how do we have a wetting and drying cycle at the bottom of the ocean? Now, once again, supercritical carbon dioxide comes to the rescue, right? So now remember I was saying supercritical water can absorb enough oxygen to support a flame. So as I say, the secret sauce once again is supercritical carbon dioxide. Now, there's two things going on with supercritical carbon dioxide. One is that a little bit of water will dissolve in supercritical carbon dioxide, but importantly, as well as the water actually dissolving in it, you also have a suspension of little beads, little droplets of water just floating around within the supercritical carbon dioxide. Now, if these droplets contain amino acids and hit a surface, they'll spread out. Now you have to take my word for it, when a droplet of water is spreading out on something, it will tend to evaporate and the activity will diminish. So a droplet of water will hit the wall, start to evaporate, the concentration of water will diminish, and it will actually prompt this reaction here that we're talking about. Then after that peptide has formed, the next step is that another droplet of water will bash into that, and maybe it will continue the reaction like that wetting and drying cycle, or maybe it will bounce off and grab that molecule, or maybe that molecule, that partly formed peptide, will just float off the wall into the supercritical carbon dioxide. But notice, you can actually have supercritical carbon dioxide helping in the formation of these peptides. So now we have a situation where we can form amino acids and bond them together. The next step, we just don't want any random linkage, but we want it directed so you can do something. Now, here we rely on the fact that amino acids can catalyze reactions. We just want them to catalyze the formation of particular peptides. You could in fact have one peptide that catalytically forms one bond, and then another peptide catalytically forms another bond, and then another one does that, and at the end of that you actually have the first peptide. So, you know, those sort of things that you did when you were young, the number you originally thought of, you know, that sort of thing. So that's what's called the notion of autocatalytic loops. Now, there's a researcher called Kaufman who developed this idea a very long time ago, but they couldn't think of ways that they could set up amino acids to naturally join together. And, well, I would suggest, well, here's one possibility now. Now, the exact details of the catalyst that takes place is to be determined, but if you have 20 amino acids, then they can fit together in so many ways to make so many shapes, we could reasonably expect they would form a shape that then catalyzes something you want. And because all of our biological life is so far removed from this original time, we're not really familiar with that style of chemistry, but maybe it's possible. So we're thinking of 10 peptides made. There's some linkages that are deliberate, some are accidental, but at the end of the day, you have some peptides you want, and those peptides will make more of themselves. Now, the nice thing about current amino acids is you have 20 possibilities to fit things together. Partly it's also good that you can chain the amino acids together. But in a sense, that's nice that there's only 20 of them. It's a large number, but it's not so large as to be overwhelming. Now I'm going to talk about information theory and chemical compounds, as I say, something inspired by this. If you have a carbon atom, and it can link to oxygen, it can link to another carbon, it can link to a hydrogen. In terms of all the chemical bonds it might have been and what it is, that bond contains energy. Just like on a magnetic tape, the magnets can be up or down, and that's how we used to encode audio onto a tape, because it can be different states. And in a sense, the different possibilities for a chemical reaction encode information. Now, but again, if you just sort of say, oh, this carbon could connect to a hydrogen, it could connect to a nitrogen, it could connect that, the combinations is just exponentially explosive. But 20 or less, okay, we're fitting them together, there's different possibilities, we might find an interesting combination that gives you a particular shape that then catalyzes another reaction. Okay, that's possible. Now I will briefly delve into information theory. Okay, now with information theory, the more surprising something is, the more information it contains. Now, but in information theory, surprise is used in a specialised way. If you roll a dice and let's say it becomes up 4, you're supposed to be surprised. Of course, we would look at the dice and say, well, it had to be something, didn't it? So maybe we're not so surprised. But in information theory, you're supposed to be surprised because it's a 4 and it could have been a 1, 2, 3, or a 5, or a 6, right? So that's the idea of information theory, the comparison between what is and what might have been. And the more things that might have been, the more information it contains. So from both a philosophical and a mathematical sense, information is related to the ratio of what might have been divided by what actually happened, right? So that's one way of thinking about information. Like something that can be heads or tails, or the magnetic field can be up or down, that's one bit of information per thing that we store. Now, perhaps you're aware of all those motivational speakers telling you that failure is just feedback. I don't know if you heard that one, but I think that's more of a tool to keep yourself motivated in the face of failure. Now, as I say, from an information theory perspective, if things go surprisingly badly, that's information. But you might not think about it. If things go surprisingly well, that's also information, right? And if let's just say you just expect to get success, but someone's going, oh, that's really fantastic, I'm going to tell 10 of my friends about it. And all you were wanting to do was hoping that person would agree with you, and then they go off and think, oh, I'm going to tell my 10 mates about this, is really good. Well, that's both successful and perhaps surprisingly successful. So as I say, failure or success, to the extent that it's extreme, contains information. And in the same way, if a horse wins that you weren't expecting to, that's information. If a politician does something you don't expect, that's information. So notice from this point of view, the unexpected has more information. And you know, there's theories of science that sort of build on that. But anyway, getting back to chemical compounds. So amino acids, basically they combine, they search out the possibility of shapes that might catalyse reactions. And you know, for early life, we can expect that even a subset of those 20 amino acids will still be enough to form a myriad of shapes that can help to catalyse the formation of peptides. Now, amino acids are unique in a lot of other ways. There's relatively few of them. They can chain together or polymerise. We've just gone into that whole story. They can form a myriad of shapes to facilitate catalysis, and they can be both acids and bases at the same time. In chemistry, you can have a series of reactions which filter out the amino acids, and it's possible to imagine different areas of a deep ocean trench, perhaps with different pHs or other characteristics, acting to filter out the amino acids and then catalytically join them together. Now, what we're talking about is the chemical precursors to life existing in a soup, but there's no cells as yet. Now, Professor Lane notes that cells are about setting up a particular chemical environment within the cell different to the outside environment. But needless to say, if the prevailing chemical environment is just what you need, well, you don't need a cell. You can just have all these molecules just floating about doing their thing. Now, Professor Lane, he does actually see viruses alive, and that's sort of one element of the debate. Are viruses alive? It's just that they do not generate the chemical environment, but must rather rely on being set up by other means, which is currently other forms of life when a virus sort of enters a cell. And let's see, open that up. Okay, so now we're going back to our cells. Now, remember I said prokaryotes over here, which are simple cells. So we can imagine that in the first step, you have just all these molecules just floating in the soup, doing their chemical reaction. The first stage is then they get encompassed into a cell, and we have our prokaryotes. And then the next step is the prokaryotes get more complicated. They have a nucleus, they have mitochondria, they have lots of other things. And then the next step beyond that is that you take your eukaryotes and form multicellular beings like us. So you can see there's a chain. At each stage, a bunch of individual things clumped together in sort of an envelope. And that was the first step of life. Here's our free-floating chemical reactions just doing their thing, and then there might well be a cell with a cellular membrane, and the advantage of that is higher concentration. But you have to assume that even without that high concentration, you can still sort of get by. It's just that cells are better. At the moment, you really do need a cell. There's no way around it. Okay, so now Professor Lane, he also reflects on the mystery of eukaryotic cells, how you go from a prokaryote to a eukaryote. Now, I don't have time for that. He goes into some quite considerable detail there, and I invite you to check that out. For me, the thing that intrigued me is what are the first chemical reactions that store information and are that first stepping stone on the way to life. For me, that's more interesting, but yeah, Lane does look into how did eukaryotes come about. Because some people will say, sure, life itself is a grand challenge, but how you went from prokaryotes to eukaryotes is also another grand challenge, depending on where you want to emphasise things. Now, these days, if you have this soup that I'm talking about, currently living microbes will feed on its nutrients and there won't be any left. But in a sterile environment, the chemical reactions I'm talking about, even if they're slow and inefficient, they can still take place and persist for long enough that they will actually prompt reactions that prompt their own reactions, even if it's only building up very slowly. Now, there was an evolutionary biologist by the name of Leslie Orgel, however you say his last name, who had two rules attributed to him. The first, that whenever a spontaneous process is too slow or inefficient, a protein will evolve to make it more efficient. The second is that evolution is smarter than you are. Well, let's not worry too much about the second one, but the first one is the other important one. A sterile environment is one where such improvement can take place. We have something that just more or less works, and as it explores the space of possible reactions, it can make things better. Now, and that is a different one to the environment we have where you really don't have anything of such sterility. Now, we've imagined a situation where peptides spend their time making other peptides, but what we want is that we want to synthesize other metabolic chemicals which help in the synthesis of peptides but are not amino acids themselves. So the first of such chemicals would be ATP and its variants, which means that peptides could be synthesized without the need for them to attach themselves to a wall, or in more advanced things we say there's got to be mineral or clay that align the molecules in a particular way and help the reaction. Beyond that, we could also have DNA and RNA assisting in the catalytic process, where later on we get onto that chemical specialization that we see in current life. Now, at some later stage, we can imagine cells developing where they increase the rate of reaction by concentrating the chemical reactants. So that's the step that I am focusing on to outline some of the steps going on to other forms of life. Now, I'm reaching the end of this talk, but before closing off this talk, I will mention some ideas about alternative forms of life, alien life that might exist on other planets. Now, in an earlier version of this talk, I made a point of going through some possibilities, and I think some people might well be checking out this talk based on the fact that I might be saying a little bit about alien life and other possibilities. Now, one thing I have to say is I don't have the time to go into the possibilities of life that is based on something other than carbon chemistry. So you'll have to obviously talk to someone else about that, or maybe in a few years I'll actually give a talk and cover that side of things. But even if you assume carbon chemistry and some of the ingredients I've outlined, there's still scope for a lot of variation and things going off in rather different directions. Now, we can imagine that some things like carbohydrates carry over. And the interesting thing about carbohydrates is carbohydrates have got carbon, oxygen and hydrogen. Who would have thought? Now, vitamins don't have amines in them, so they got that one wrong. But carbohydrates, there is actually a match between what they are and how they are described. But the thing about carbohydrates is, apart from ATP and the other molecules, we also say, they contain energy, but they also give us structure. If you turn a glucose into cellulose, that's structural, okay? So regardless of the chemical details, we might still have sugars, glucose, cellulose and so on performing similar tasks to what they have at the moment, and that's separate to the biochemical machinery behind that. Now, also you could imagine that we have cell walls that have a similar chemistry to what we have at the moment, but there might be some very different chemistry making those cell walls while they're more or less what we have at the moment. But also I want to look at the actual chemical machinery that runs life. The first is at the beginnings of life that I've described, which is just proteins making proteins making proteins. Maybe they end up in a cell and we never get DNA and RNA in the way that we imagine them. So it's sort of basically contained bubbles of protein reaction. And that's a possibility of life that doesn't get as far as it has on our planet Earth. So you've got cells, but they're not driven by RNA and DNA the way they are. Now, another possibility is that there's a different set of amino acids running that life, and also it uses DNA or RNA, but their encoding scheme is different. So there's similar, catalytic protein chemistry, but different amino acids, different encoding, different stuff going on. Now, it's possible we have DNA and RNA because DNA is really the only chemical that really forms a nice neat spiral, and you can't find any others, okay? Maybe there are other chemicals that will store information as well as DNA. If not, maybe all alien life will be pushed towards DNA because it's really the only game in town, I guess you would say. So maybe there are other ways of encoding that information apart from DNA? Maybe. So one thing that I've often wondered about is whether there might still be life around which uses a different DNA encoding with a more limited set of amino acids. Remember I said that our current encoding uses 3 base pairs to encode proteins. Maybe you have DNA but it uses 2 base pairs to encode 4 amino acids or something like that. But as far as I can tell, everything alive on planet Earth uses DNA and RNA encoded in the way that we are familiar with. Everything on Earth that is alive does that. That is the legacy of the so-called last universal common ancestor. So having briefly looked at some thoughts on alien life, I will actually come to a close. Now, I've painted a story which is on the one hand, I hope, reasonable, but for so many things I do not have proof, and a story of varying detail. Now, can pools of supercritical carbon dioxide develop on ocean floors in trenches? While they must have the needed carbon dioxide by definition, can they incorporate the needed water, hydrogen and other components? Can supercritical carbon dioxide sustain a Muller-Urey style of amino acid synthesis using static electricity? Can we either imagine a way of concentrating the amino acids or accepting the wasteful side reactions along the way? Can we make use of droplets of water hitting a surface and evaporating to prompt peptide formation, an undersea variant of that wetting and drying cycle supposed to happen on the surface of Earth? Can we have peptides randomly form which then generate more of the same, with an error rate letting them explore the space of catalytic possibilities? So this story was originally prompted by an appreciation of the information content of chemical compounds, as I say, writings of Predator, and also I developed a fascination for Kaufman's autocatalytic loops. So I guess you might say it's been a somewhat directed investigation based on what I hope is possible, what I find intriguing. but it's full of unknowns. I don't have evidence for it, but I hope you find it to be an intriguing possibility, and in talking about my possibilities, it's illuminated how life actually happened and how it might have formed. And obviously there's Professor Lane's perspective as well if you want to have a look at that. Anyway, thank you for your attention. I hope you found it interesting.